Hello everyone and welcome to the third part of DARSim simulator tutorials. If you have not watched the first and the second part, please go and do so because you will need those informations in order to be able to follow on this video as well. Now, in this video we will discuss what the input files look like and what are the keywords that we are using inside those input files. We will use a heterogeneous 2D test case to run via DARSim simulator, which is based on the model from SPE10 and the top layer. So as the first step, please go to the GitLab repository of DARSim examples, gitlab.com/darsim/examples. Then go to the multi-scale course folder, inside that heterogeneous two-phase flow. In this folder you'll see three example files. The first one, immiscible, is the main simulation input file. The third one is the simulator settings. I have already explained in the previous video. You will also need this file, the second file, permeability of the heterogeneity of SPE10 top layer. We will need that because this time we are running a heterogeneous test case. So please download them. I have already downloaded and put these files in a specific folder anywhere in your computer, it doesn't matter. First we want to run this test case and see the result. Then we will go into the input files and see what every keyword means and if we can change them and see what it does to the result of the simulator. The test case that we are going to run, as I explained, is the SPE10 top layer, a 2D heterogeneous model. This is the permeability, the heterogeneous permeability that you see, and this is the color range, the range of the color bar. I am putting one injection well at the bottom left corner with 500 bar fixed of pressure, and then I'm putting one production well on the top right corner with 100 bar for pressure. I'm discretizing the system to 220 times 60. It can be again any number. This is just my choice for simplicity, and in total you have 13,200 grid cells. In order to run it, please go to your Matlab, make sure that you are on the SRC folder and type DARSim res sim. Please make sure that the capital and small letters are written properly, and we give two input arguments, two strings. The first one is the path, the full path to the input folder that we are running this test case on, the folder that you basically downloaded those three text files. The second input argument, the string, is the full name of the main simulation input. In this case, in this example, is immiscible.txt. This name again can be anything that you want, it does not matter. And then you press the enter. And then we wait till the simulation is done. But before we do that, I just want to explain. So the information is printed as some text on the command window of Matlab. It says reading permeability files, so that means that it's a heterogeneous test case. The name of the simulation, which you will see later where it came from, some characteristics of the reservoir geometry, and some information which we will go through later. So this will continue to run. I'm gonna pause the video. I will get back to you when this is finished. Okay, and the simulation is done. The simulation ran for 2000 days, and we have asked the simulator to print the output files every 20 days, in total 100 reports. So if you go back to the folder, you see now there is an output directory inside. Now there are some TXT files, some reports that we don't want to go into details of them right now. What is important for us is the VTK folder. If you go inside the VTK folder, you see there are about 100 VTK files named and then numbered from 0, which is the initial state, the initial condition of the system without running and solving the system. And then every report you see that there is a VTK file. Now we want to open these VTK files inside the ParaView. Please open ParaView. When it's open, choose this icon, open, and then here you should navigate and browse into the directory where those VTK file exists. For sake of simplicity, I would do this. I would copy the entire path. On Windows, this is how it is done. And then go back to your ParaView open file window, paste the address, and then press navigate. Then you go directly into the location where the VTK files exist. Now you'll see that ParaView, due to the numbering of the files, group all these VTK files that are familiar into one group. This is what you want. So choose the group of the VTK files and press OK, and then press apply. Now you can see the extent of your 2D domain. You can zoom in with your scrolling of your mouse wheel, front and backward. So now I am zooming a bit. Now you can choose the option of Perm X, which is the permeability in X direction. For now, all the permeabilities in X, Y, and Z direction are the same. It's an isotropic system. Choose the Perm X and then choose Surface. You can press Shift, and with your holding the right click of your mouse, you can move this 2D domain into up and the lower part. So I'm doing this just to avoid the overlapping with the color bar. You can use this option, use log scale when mapping data to colors, to change from a linear mapping scale to a log scale. This way you can see more of the contrast of your permeability field. I also recommend, not necessary, but I also recommend to choose the color map. This color map does not reveal all the contrast properly in sake of visibility. So press this option, this icon, and then choose Jet. This is a color map that has more range of colors. It reveals more heterogeneity contrast, and press apply. Now you see the permeability and the color bar also from 3 times 10 to power of minus 18 up to 4.6 times 10 to power of minus 12 in SI units. Now please choose the variable P1, which is the pressure of the phase 1. As we don't have any capillarity in this test case run, the P1 and P2 both have identical values. P1 is basically now the pressure of your system. Also, again, I recommend you to choose the color map Jet, as it has more visibility in terms of the contrast between different values. Now, what I would also like you to do is to choose this option. This option rescales the range of your color bar across all the reports or time steps, and then press rescale and disable automatic rescaling. Now you see that your pressure ranges from 100 bar or 1 times 10 to power of 7 Pascal to 500 bar or 5 times 10 to power of 7 Pascal. This is the initial state or the initial solution. We have not solved the system at this point yet. You could see that out of 100 reports, this is report number 0. Now, if you press this icon, this is the solution, the pressure at time step 1. Actually, I should say report 1. As I mentioned, 2000 days of simulation time, 100 reports, every report is 20 days. So this is the end of the first 20 days. If you press this again, you go to the 40 days or the second report, third report, fourth report. You can also press the play button to dynamically and in an animation way see how the simulation progress and changes in your pressure solution. Now I'm pressing it, it goes, as you see, it's dynamically changing from 0 to the 100th report or the 2000 day, the entire simulation time. You can also go back again to the initial state. Instead of pressure, choose saturation of phase 1. This is the injection phase that we started to inject from the bottom left corner all the way. We'll push the second phase, in this example oil, through the production well in the top right corner. So we choose saturation of phase 1. Again, I would recommend you to choose the Jet color map, apply. What I would want you to do, same as pressure, go and press this icon, to rescale the column map across all the reports or time step or the entire simulation time. So press this icon and then rescale and disable automatic rescaling. Now you see that your saturation scale is from 0 to 1. Obviously at the initial state there is no phase 1 or water because it's a water flooding test case. There is no water in your system. Now if you press this icon, this option, it brings you to the first report, second report, third report. So this is actually 60 days, 80 days, now 100 days. You can also press the play to see an animation of how simulation progresses. And you can see that this is how your saturation front for the phase 1 or water progresses and sweeps the oil or the second phase across your domain. Obviously the front that you see is due to the permeability and heterogeneity contrast in your system. Now we want to go back to the folder and we want to open the input files and see how they look like. So I am using Notepad++ on Microsoft Windows. Feel free to choose any editor. It's your choice. It's not important. So first of all, open the immiscible.txt text file. Now there are certain keywords that we will go through them and we will check them one by one. All the keywords will be in capital letters. Underneath every keyboard you will mention the configuration that is needed for that specific keyword. Now the first keyword is title. There is nothing that this keyword does specifically inside your simulator. The only effect that this keyword has is adds the name, in this case SPE10T or SPE10 top, to all the output files. So if I go to the output folder VTK, I see that there is an SPE10T connected or named or written in the beginning of all the files that you have. It's not just that, also other output files which we may explain in the future videos. The second one is the dimension. In this dimension you give the scale or length of your system or domain in X, Y and Z in meters. So in this example this is a 220 meter times 60 meter times 1 meter. Obviously this is actually a 3D model, but because it is discretized only in 2D dimensions, it is considered as a 2D domain. So it's almost a flat model. The next case is spec grid. Underneath the spec grid you give the number of grid cells in X, in Y and in Z direction. So in this example this system is discretized into 220 times 60 times 1. When you have only one grid cell in Z direction, this makes it a 2D discretization. The next case is total time, written exactly like this with an underline in between. In the total time you can specify the amount of the simulation time that you want it to run. So in this case you have 2000 days, 0 hours, 0 minutes and 0 seconds. Make sure that if you're adding hours, minutes and seconds, which may not be necessary, to make sure that you have written days, hours, minutes and seconds in capital letters. If you do not write any of these, just write 2000. By default the simulator assumes that you meant days, so this will be 2000 days. So let me bring it back. Now for your permeability you have to specify some keywords. The first keyword is permeability unit. So the permeability that you want to specify, either homogeneous or heterogeneous, might be in meter square in meter squared, that you write it this way, M2, or DARSI, capital D, or milli-DARSI, small letter m and capital D. If you don't specify anything, you do not include this keyword, by default the simulator assumes that it's in meter squared, so SI unit. The next keyword is permeability scale. What you should specify here is either linear or logarithmic, exactly as it's written. So in case you have a permeability file that you have to read and open on in your simulator, it might be the case that the data that is given to you are not in linear scale, they are in logarithmic scale. You can easily identify that, recognize the logarithmic scale if you have many values in negative. So if those values are negative, that means that these values are in logarithmic scale. In this case, we're going to keep it saying linear. If you do not specify this keyword, by default, the simulator will assume linear permeability scale. Now, in order to specify the permeability, you either have the option to give a file to the system or to specify it yourself. For a homogeneous test case, so not this one, but for a homogeneous test case, what you have to mention is just the keyword permeability X and the value in this unit that you specified above. So in this case, it's going to be in millidarcy, so assume that I want permeability to be in 10 millidarcy. Then I type 10. If I specify my permeability unit in meters squared, then I have to mention, for example, 1e minus 14 if I want it to be 10 millidarcy. Obviously, I need to do the same for permeability in x and y direction, and also z if z exists. If not, it actually does not matter. You don't have to do it, but I'm doing it for sake of completeness of explaining these keywords. So in this case, I am specifying the homogeneous permeability in all x, y, and z direction, all meters squared, linear scale, and the values of them are 10 to minus 40. This will be a homogeneous test case, but in our case, in this example, it was a heterogeneous test case. So what happened is that I am pressing Ctrl Z, reverting all the changes that I made. In this case, I am reading a permeability file, which I want to show you actually. So the permeability file, we go back to the root of this folder, is perm_spe10t. If you open this file, you see that there is a long list, one column of many values. These are all permeability values for every grid cell. The first three numbers, although, are different. The first three numbers are mentioning what the extent of this permeability map is. This says that this permeability map covers up to 220 grids in X direction, 60 grid cells in Y direction, and only one grid in Z direction. So this is a 2D map of a permeability for 220 times 60. Now I want to go back here. So if you want to include that file for your simulator, first of all, you need to make sure that this permeability file exists on the root and the location where the other main input file exists as well. Then what you should do, on top of the keyword permeability_x, you should write capital letters include. This will tell simulator that underneath the permeability x, what it's expected is not a number, it's the name, a complete name of a permeability file that exists in the root of the input folder. Just to give an extra information, you can also give here the full path to the permeability file. So in this case, I can even give the entire path as it's written like that. So it starts with the drive letter of my computer, all the complete path. The benefit of this way of specifying the path to the permeability file is that it might be the case that you have a heavy file and it's located on a different location. You don't want to repeatedly copy paste this file if you want to run multiple test cases. You can keep that file somewhere specific in your computer, and for every test case you can just give the entire path to this permeability file. This saves you all the space that you may have to consume on your hard drive or on your storage device if you want to copy paste and create a duplicate of your permeability file over and over again for all the simulations or all the test cases that you want to run. But here it's not very important, so we'll bring it back just to the full name of the permeability file. So we do the same, include permeability y, the name of the file, include permeability z, the name of the file. Please note that all the indentation that you see are not important for the simulator. It's not being detected by the simulator. What I'm doing, I could also write them all this way, but why the reason that I'm doing this is just for ourselves, for our own eyes, to better understand all the different keywords, and this is just for sake of a better visibility of all the text that is written on this input file. The next one is porosity. Porosity, as it given, is the porosity of your system. You give this value as a fraction between 0 to 1. In this case, it's 20% or 0.2. Now, here comes the fluid properties. So you can specify the fluid densities underneath this keyword. This is not important. I just wrote it here so you will see that the units are in SI. The simulator will not see this, and this will not have an effect. And as we have two phases, I am giving the viscosity of the phase 1, in this case water, and the phase 2, in this case oil. So 1000 kilogram per cubic meter and 800 kilogram per cubic meter. The next keyword is fluid viscosity in Pascal second. So you definitely make sure that you have written this keyword, and then you give the values for the first phase and the second phase underneath each other. So 10 to minus 3 and 3 times 10 to minus 3 Pascal second for viscosity of phase 1 water and phase 2 oil. You can also specify fluid compressibility in unit of 1 over Pascal. In this case is 0. You can also mention, for example, 1e minus 8 as a value for the compressibility of phase 1, or I don't know, 1e minus 7, for example, for compressibility for the other phase. In this case, I am just giving them as 0. This is the raw compressibility. Again, in unit of 1 over Pascal, make sure that all the letters are in capital. You can also specify a value for this. In this case, I'm putting a 0, but for example, I could give 1e minus 10, for example, as the value for compressibility of the rock. Get back to 0. The next keyword is rel perm in capital letters. This is the relative permeability configuration for your simulator. You can choose different options like linear, quadratic, or Cori, and there are some values, parameters that you can put, like the saturation, residual saturation of the wetting phase, residual saturation of the non-wetting phase, and the endpoint relative permeabilities for the wetting phase and non-wetting phase, and the saturation exponent for wetting phase and non-wetting phase. Make sure that you give the values underneath one of these examples, so in such a way that if linear is at line 79, this keyword or option is at line 79, the first value is 2 lines below, so 81, and then 83, and then line 85, line 87. This is how the simulator will run it, and this is useful because on the line above you can have an explanation and what every parameter and the value underneath it means. But first, I want to show you how the relative permeability in a general way is calculated in this simulator. So a general way of calculating relative permeability uses the Brooks-Cori formulation, which is what you see. The relative permeability for the wetting phase is the endpoint relative permeability of this wetting phase times this fraction to the power of the saturation exponent for the wetting phase. So this is the saturation of the wetting phase minus the residual saturation divided by 1 minus the residual of both saturations. And the same formula is used to calculate the relative permeability of the non-wetting phase. Now, if you choose a linear, this, I want to see if I can, yeah. So if you choose linear, this exponent, saturation exponents will be 1. If you choose quadratic, this saturation exponent will be 2. And if you use Cori, then that means you need to specify them one by one here. In this case, we use a simple example for relative permeability configuration, which is linear, and all the residual saturations are 0, the endpoint relative permeabilities are 1, and the saturation exponent are 1. Anyways, we are using linear, so they will be 1. Now, the next keyword is fluid model. Underneath this fluid model, you need to specify few parameters. First of all, the type of the fluid model that you're going to have, either single phase or two-phase. For two-phase, you can type immiscible, which means that you will have a two-phase fluid that are immiscible. And underneath, you specify the number of phases. Again, make sure that underneath this immiscible, there is first a line that explains it, and then underneath that, you have the value as the number of phases. So if this is at line 96, this is at line 98. And obviously, we have two phases and two components, water and oil. And again, there is a line in between. The next keywords are the initial conditions of your domain. The first one is the initial pressure in Pascal, which in this case, your initial pressure is 100 bar, and initial saturation and of phase 1 and initial saturation of phase 2. That means that at the beginning, there is no initial water in the system and it's all oil. The next ones are the well configurations. Every well that you configure or give as input starts with the keyword well start and ends with the keyword well end. In between these two keywords, you can specify the configurations of these wells. The first keyword is type, again in capital letters. You can either choose ing as in injection or prod or as in production. The next keyword is the coordinate. In this case, you see that you can give the coordination of the wells, the start and end point. There is different types of coordination. Here, for sake of simplicity, I just mentioned one of them, which is IJK list, which is self-explanatory. What it means is that I am putting the first point where this well is overlapping or perforating that cell, which is starts with I equals 1, J equals 1, K equals 1. And then it ends at I equals 1, J equals 1, K equals NZ. What does this mean? This means that my well is actually a vertical well if you have a bird's eye view of this system in X and Y direction, and Z is basically on the screen. You see that this well starts from the beginning, the first corner at the first layer, and perforates all the cells on the same column all the way to the top layer. But because in this 2D example we have only one layer, this doesn't matter anyways. There is only one layer, so in this example there is only one cell that this well is perforating. Now obviously for the production well, I need to give all the way the nx number. This is a parametric value. This helps you not to have the necessity to, for example, type instead of nx 200, because every time you may want to rerun your simulator with different number of grids, and then you have to also scroll down all the way to the well configuration and change these values. This gives you an easier choice just to give a parametric value of nx. In this case, nx will be 220, ny will be 60, and nz is 1. So now this shows you that this well is perforating the cell at point nx, ny, and 1, which on this map will be all the way to the right and all the way to the top. So top right and the first layer, and then goes all the way to nx, ny, nz. Again, same point, but the top layer. But again, this is a 2D system, so you have only one layer. If you had a 3D system, you would have seen that this would be a vertical well perforating different layers in a vertical manner. The next keyword is constraint. You can either specify pressure constraint or rate constraint well. But because the rate constraint implementation is under development at this point in time, please only use the pressure rate. So basically you don't have to change this. The second value that you have to give underneath this pressure keyword is the value of this constraint or the pressure. So in this case, my injection well has a pressure of 5 times E 10 to the power of 7, and my production well has 1 times 10 to the power of 7 Pascal. This is in Pascal unit. The next is the formula, the type that the well flux is calculated. In this simulator, the well flux is calculated via the Pieceman well model, which is productivity index times the density times mobility times the pressure differences. Now you can specify the formula either as PI or WI. I would recommend WI because when you choose WI, the formula is calculated as WI times rho times density times mobility times the pressure difference, and then is multiplied by the volume of the cell that this well is perforated inside. And then you give the value. At this point in time, you don't have to change the value of this keyword, but later you can play around with this. Just to let you know, the higher the well index of a well, the better the conductivity between the well and the system. So if the well is damaged, you have a skin factor, or there are some plugging of the perforations, then this value should be defined lower. If you have a very good conductivity between the well and the system, then this value can be higher. Now please go back to the folder and open simulator settings.txt. There are a few keywords here that are also important to notice. The first one, if you remember, I mentioned that the simulator reported 100 files as an output from this simulation. This was specified under the keyword reports. Here you can specify how many output report files you want to have. You can also specify the value 0. This value 0 makes it in an unlimited manner. That means that at every time step it specifies or it prints the output file from the result of the simulator. But if you want to have the output files of equal time interval, it's best if you mention how many reports you want to have. In this case, 100 reports. The next keyword is min max dt in capital letters. This is self-explanatory. So obviously what it means is that you can specify what would be the minimum value of your time step size and the maximum value of it. By the way, this is in days. So your time step starts with 1 day and it can grow to a maximum value of 30 days. However, in this example that we ran, we could only go to a maximum of 20 days because we are mentioning 100 reports and the entire simulation time is in 2000 days. That means that the simulator will override this value and uses 20 as the maximum number of days for the time step size. The next keyword is the output in capital letters. At this point in time, DARSim can only print outputs as VTK for the ParaView visualization software. So please just type this as it is. The next keyword is used for the coupling strategy that we have between the equations. In this example, we are using the fully implicit method. And the keyword for that is FIM in capital letters. Underneath FIM keyword, you can give 3 lines of configuration. The first one is the maximum number of iteration. In this case, we have 20. That means that if the iteration loop continues and it does not converge after 20 iteration, it restarts the iteration loop with chopping the size of the time step in half. If it does converge in less than 20 iteration, it assumes that the system is solved and goes to the next time step and continues with the simulation. The next line is basically the tolerance, the convergence tolerance for the residual of the equation. So this means that if the norm of the residual of the first equation is less than 10 minus 5, convergence is happened. If it's bigger than 10 minus 5, then convergence has not happened. It has to start, continues the iteration, or even restart the iteration loop. As you have two equations, you can specify the tolerance for the residuals in separately from each other. In this case, they are identical, but you can specify them different and separate from each other. The residual of the second equation, also the tolerance for it is, in this example, 10 minus 5. So if the norm of the residual, by the way, divided by the initial residual, is less than 10 minus 5, the convergence has happened. If not, it continues iterating. The third line is the solution norm tolerance. So your update of your unknown. If the update of the first unknown at every iteration compared to the initial state is less than 10 minus 4, then convergence has happened. Is it bigger than 10 minus 4, convergence has not happened. We can specify this for the next or for the second unknown that we have in our system differently. Please note that we are solving a multi-phase flow, two-phase flow system. So we have the equation of mass balance for phase 1 and phase 2. So you have two equations and two unknowns. So you can specify the tolerances separate from each other. The next keyword is linear solver in capital. At this point in time, you can use the keyword, the option direct, to use basically the Matlab / operator as your linear solver for your system.